Hello everyone. The next topic that we will see is the continuous time finance or continuous time asset pricing theory or risk neutral pricing in continuous time. Before we go to risk neutral pricing, first we will try to apply the similar process as we have done in discrete time. Okay. Recall that in discrete time we first considered the binomial asset pricing model and we considered derivative which has an underlying as the risk free assets in the binomial asset pricing model, and through replication and with the help of no arbitrage pricing theory we could find out what is the initial price and prices at all intermediate times along with the delta hedging rule which will replicate the short position that you had taken in the under a derivative, right. So, you just recall that portion, right. So, what in a one period model what we have done is that there were two quantities delta naught x naught which needed to determine, which we determined by equating the evolutions and setting it up a 2 by 2 system of linear equations, and by solving which we get the we have got the solution, which is basically what is the initial price and what is the replicating strategy for replicating the short position in the underlying asset. Similarly, in a two period model, if you recall, there were 6 unknowns, 3 of them are the underlying positions and 3 of them were the prices during that time 0 and time 1 in a two period model, right. So, this is what we gave via the binomial pricing algorithm, and we found out these quantities, and hence because this is the price that is needed along with the hedging strategy to replicate the short position in the derivative. So, the short hedge we simply call that as a short hedge. Replication of short hedge or the value or the wealth that is required to replicate a short hedge position was what we call as the no arbitrage price, because that is what will give you a fair price, because that does not give any one party, whether it is long or short holder, any undue advantage is not being given by such a price. So, that is what we call as a fair price. The fair the idea in our context is the no arbitrage price. So, based on the no arbitrage principle, so that is why that is called, we call that as an arbitrage pricing theory approach to find the price of the derivative. Later we did put this, after defining the two quantities P tilde Q tilde, which we called as the risk neutral pricing measure, we tried to put this in that framework and gave the risk neutral pricing formula. Okay. Here also in continuous time also we are going to do almost similar thing. First what we will take up is the first part of it, which is basically the APT approach, or by replication or by equating the evolution, how do we find the price or what is the price. Okay. So, that is the part that we will take. So, that is what the first part of this ideas that we will carry over, because then you can connect with your discrete time model how you have done that, right. So, what we have now is that at the continuous time all the assumptions that was there in the discrete time model holds true here also, which means there is a frictionless market where we assume that the bid ask spread is 0, any amount of quantity it can be bought, it can be sold, and the interest rate for buying and selling, which is borrowing and lending, is the same. So, all such assumptions that we had it in the binomial model remains true. So, what is the different assumptions that we are making here is about the evolution of the risk free asset and the risky asset, because there the time was discrete, here the time is continuous. So, you need to describe how the prices at various times are given. it could be given simply as a complete expression, or it could be given in an equivalent way to if you describe the how things evolve from one time to the other, then that is an equivalent way of description. And in finance, as you might have understood or you might have seen, that we prefer the later one to describe the evolution, to give the asset price process. Okay. So, in that regard, recall this processes that we have mentioned, right. So, we said that dxt, or now I may call this as dst, as alpha t st dt plus sigma t st dwt, okay, where this and also you could have a d bt, which is some RT bt dt, right, these three quantities. Okay. So, these three quantities alpha, sigma and RT, right, if they are adapted. Okay. And what we have the underlying ones? Underlying ones is there is a Brownian motion and there is a associated filtration, or there is a filtration for the Brownian motion, and there is a timeline, so in which you are considering in this model. And we said that this model, of course, we know what is the expression of ST in this particular case and what is the expression of BT in this particular case. So, this DST expression is what we said that uh, can be used to describe almost all processes with the properties that they have continuous paths, has no jumps and driven by a single Brownian motion. Okay. Whenever alpha t, sigma t are adapted processes. Okay. Similarly, the second quantity which we wrote here is, in general, it could be taken as adapted processes. Okay. So, this is you could think of as the the evolution of the risk free asset, which is less random than the randomness in ST, because the randomness in ST is also contribution from this dW term, which is Brownian term, which can oscillate very to a large extent in a even small interval of time, because this is normal distributed random variable oscillations, right. So, because of this property. So, this is the general setup. So, this is what along with the assumptions, if you assume that there is a risky asset which follows the dynamics given by the first equation, and there is a risk free asset which follows the dynamics given by the second equation, then this becomes a more general model for which can be applied in almost for to denote or to define the evolution of almost all processes which with the required characteristics, right, for S and V, right. But for simplicity, because this will involve alpha t, sigma t and adapted processes, a simpler case could be when these three quantities are non-random. Okay. The simple cases, these are non-random quantities, this what we talk about, this alpha, sigma and R. Okay. Then it could be, we could make simply this as time dependent. Now, the simplest case is they are all constants. So, the simplest case of this dynamics is what they are all the constants, and we will be content with this in this particular course. Okay. So, you can make it slightly more general, non-random, and its theory is not going to be so complex, but the expression, writing and everything. So, this is constants that we are making it. So, that means when we have the constants here, then what actually, if you recall, the solution of this, the first equation and the second equation, the first equation, then it gave a simple geometric Brownian motion, and in the second equation it is simply the simple ODE in that particular case, and that gave solution as e to the power RT along with the 1. Okay. So, let us describe that as the model that we are considering, and that model is what would be called as or BSM. As opposed to the binomial model in the discrete time case, what we have here is the Black-Scholes-Merton model, which was traditionally used to be called as simply as Black-Scholes model. That is how you would find in many books and references and other places. But if you go back and you will see that actually the Nobel Prize was awarded for the works of all people, all three. So, of course, we might like to call them as simply as Black-Scholes-Merton model. Okay. So, this is the Black-Scholes-Merton model, which is what is the continuous time thing is that here, right. So, now what we have, the description is you have a risky asset whose description is given by some alpha times st dt plus a constant sigma times which is non-zero st dt under some s naught. Okay. And if you know that the solution, okay, we will write in a moment, okay, and the risk free asset in this particular case is, we could call this as simply dBt as rBt dt, okay, with conveniently b naught as equal to 1 and with conveniently here S naught, we can assume a generic S naught, this greater than 0 is what we may prefer, because if as you know, in these two particular cases equivalently this can be represented as St as S naught times e to the power sigma Wt plus alpha minus half sigma square t is what is the solution. And for the second case, it is Bt, it is actually B naught e to the power or t is what then you would get. Okay. Now, so whether you represent it as if the price process of the underlying asset is given by this St and this Bt for the risk free asset, and or you are writing in terms of the previous two equations which are effectively SDEs. Of course, the second one is actually an ODE, but you can still call that as an SDE. So, this is given by the SDEs. Okay. So, if I do not assume S naught greater than 0, right, I know if S naught is strictly greater than 0, then for all ST this will be strictly greater than 0. If S naught is equals 0, then this is going to remain 0 for all time t, right. So, to make a meaningful discussion, we simply assume that S naught is greater than 0. It is not necessary that this is the case here, right. So, it could also be S naught greater than or equal to 0, and similarly for B0 equal to 1 for convenience we take, it could be any starting point, and as you know, the solution is simply this, okay, in this particular case, right. So, this is what is the description. All other assumptions with regard to the market under which these two assets exist remain the same. So, what we consider, so this is in some sense called the classical BSM. Okay, the classical BSM, I mean in sometimes it we mean that the constant coefficients, the in the SDE for risky assets, the drift coefficient is constant and this diffusion coefficient is constant, and the SDE for the risk free asset, the coefficient is also constant. And what is the risky assets that we have in mind when we are writing down this? This is typically a stock. Of course, we could use this model to model any other price process which will follow this pattern. ST is given by this, right? And SD is what? Distribution now? It is a log normal distributor. Essentially what? So, this is log normally distributed random variable. This ST is log normal distributed because there is a WT here which follows a normal distribution, and this is e to the power some constant times W plus some constant, right. So, that is essentially a log normal distribution. So, ST, right. By the way, this S naught is typically assumed to be non-random, that is we also make it clear. And ST is log normal distributed random variable. You can find its mean, variance yourself. Okay. So, exercise is find mean and variance of ST. Okay. You can try and see like what is its mean behavior, what is its variance, how it is distributed as. Okay. So, this is the model. So, this is the classical BSM setup where the and risk free asset, by the way, we mean it could be a money market account, it could be a bond, it could be anything, something which has this as the dynamics, which means that, oh sorry, very sorry, like this is, there is a confusion here that the sigma ST is dWT. So, there is a Brownian motion. So, you have a probability space on which we have defined a Brownian motion, and there is a filtration for this Brownian motion with the required properties as we defined earlier, and we have the assumptions about the market and the assumptions about the behavior of or the evolution of risky and risk free asset. All these things is what defines or describes the BSM model. Okay. So, now that we have described the BSM model, let us look at the case where the first part of this exercise that we will try to replicate, what we will see. Now, let us look at as a first part how the portfolio values evolve, right, in such a dynamics case. Okay. So, what we have, see portfolio or the wealth. So, what we have these these dynamics given, and we have what we take is at t delta t to be the our position in the risky asset, which is stock, right. So, this is basically the number of shares of the stock, which in this particular case is the risky asset. Okay. So, this position can be random, but what we require is in that case is this adapted, this be adapted to the filtration. So, this position can be random, but when you reach time t, this value of this should be known, so that from time t to t plus you are going to take this position. So, this position should be known at that point of time. Recall, in discrete time binomial model we had this delta n's, delta naught, delta 1 h, delta 1 t and so on, where once you reach to that particular node, you know what is the value. Similar, that is what is essentially the adapted process case, right. So, this is what we have, the adapted process, right. Now, once, so at time t, okay, so you say that you have at time t, you know, so the wealth or the portfolio value, suppose if we call this as xt, the wealth is xt, then you take delta t as your position, right. So, which means out of this xt, how much you are going to invest in the risky asset? it is delta T S T in stock and the remaining amount, which is x t minus delta T S T in say stock we said no. So, in money market, or bond or risk free. Okay. So, in risk, this much you are going to invest in the risk free asset, right. So, this is what, so this is your decision. What this delta T portfolio position process delta T gives is that at time T, if your wealth is x T, then out of this x T you are going to invest delta T S T in stock and the remaining amount is in x T. So, you are not keeping anything with you. So, you have to you are investing everything there into this. Okay. Now, so how this wealth evolves, right? We can write down the wealth which is changing in a small interval after t, which is what is we typically write in informal way as dxt. Now, the contribution of this would be from two sources. One is the in stock, our position in stock, the other is our position in risk free asset. Okay. In stock, we had a position of delta T ST, which means delta T number of shares ST. Now, this ST has moved from ST to ST plus something, right. So, which means that moment is essentially, so the evolution of this component of our wealth is basically delta T dST plus the other component, since it grows at the rate R dt, right. So, if you have Bt, then it is R Bt dt. So, this is delta T St R times dt, right. So, this is the evolution of the wealth. Okay. Now, you can draw a parallel to your discrete time thing. Okay. So, let us see in discrete time what you had, you recall your x n plus 1 was equal to delta n s n plus 1 plus 1 plus r times x n minus delta n s n, right. Now, what you can do is that you can write down this in the form as x n plus 1 minus x n equals delta n times S n plus 1 minus S n plus R times x n minus delta S n times, right. So, you can see a parallel, right. So, here the natural time step was 1 unit. So, the difference is in x n plus 1 minus x n, delta n was your position, the difference in S n and the R 1 unit, because this is 1 unit. So, this would have grown by this, that is precisely right. So, you can make a connection to this and see that this is really the, when you make this time unit as an infinitesimal quantity, then what you get is precisely this equation, right. Now, once we have this equation, now you can try to simplify and do and try to understand a little bit. So, delta t. Now, dst I can substitute as alpha st dt plus sigma st dwt, right, plus this as it is you could keep minus delta t st dt, which is essentially r x t dt plus delta t times alpha minus r s t dt plus delta t times sigma times s t dwt is what then you would observe. Okay. Now, this is the terms appearing on the right hand side here, you can try to understand what each one of them mean, right. So, there is the first term right. There is a first term, there is a second term, there is a third term. So, what does this actually depict? As you can see, the first term is basically the average underlying rate of return for the portfolio, which is given by R times XTDT, right. And the second term is basically the risk premium, right. For going to the asset ST, right, this alpha minus R is the rate of return of the risk free asset and alpha is the rate of return of the risky asset. So, for taking the risk free risky assets, this is the risk premium that you are having it here, right, which is obviously proportional to the position that you are taking. And the third term is basically a pure volatility term proportional to your again your position and the size of the stock investment, which is delta TST is what is, right. So, this is the pure proportional term. You see DW is essentially W is normal. So, DW, so it is a difference in the normal. So, this is a pure volatility term, whereas the first two terms which has DT terms mean now by now you understand the meaning of this DT terms. So, this is more certain than DW term, because this at least in the short interval you can predict. That is how the ODEs are formed. Okay. And if you perturb with the random noise is what you get in SDE. So, this is of that nature. So, these three terms you can understand as if this the evolution of a portfolio value is given by three component. One is the average rate of return that you expect, the other is the risk premium, the other is the volatility term, right. Now, we often shall consider the discounted stock price process and the discounted portfolio process. So, for which what does that mean? So, we often consider rather than XT and ST, we consider the discounted value of it, so that you are bringing everything at single time point unit you are looking at it. Okay. Now, so this is essentially what we mean is this quantity is what we often look for, e to the power minus RT ST. If I consider this to be a function of T and ST, right, this is actually a function of T and ST. So, what is the function here now? Ftx is e to the power minus RT times x. So, my Ft in this particular case is, as you know, will be minus R e to the power minus RTx, and my Fx is e to the power minus RT, Fxx is 0, right. So, this is what you have it here. Now, if I apply Ito's formula here, what we will get is that Ft of essentially T and ST dt plus Fx of T ST dst plus half Fxx T ST dst. Whether whatever be the thing, it is always advisable to write this in the explicit form and plug in the values and then try to simplify. Now, what you would get here is that minus R e to the power minus RT ST dt would be the first term. The second term would be e to the power minus RT dst. Of course, the third term would vanish. So, this gives me alpha minus R times e to the power minus RT ST dt plus sigma e to the power minus RT ST dWt. Now, if I consider this as the process, right, this is the process, this is what you are writing. Now, look at the dynamics of dst and look at the dynamics of the discounted process e to the power minus RT times ST, right. What you see is the change is only here, the process. So, this process is e to the power minus r t s t. So, the process appears on the right hand side in these two places also. So, there is this is the process that you have on the left side and the right side, right, but the change that happens is in the mean rate of return. So, what actually when you have a process and if you look at the discounted process, what happens, the mean rate of return is reduced by the discount factor, which is r here. So, alpha is getting reduced by alpha minus r. So, these are just observation that you make a note, which is this is what is going to be useful also when we go ahead. And similarly, d e to the power minus r t x t you can use by the same idea, right, by the same idea. So, what you would get x t. So, instead the functional form f t x is remains the same, f t, f x, f x x everything remain the same. The line here, if I apply the Ito's formula, then what you get is that. So, ultimately this will turn out to be in the same form as above, but with S t replaced by x t, because x is the portfolio process that you have here. Now, if I substitute for my d x t what I have here, right, you would see that this delta t terms alpha minus r e to the power minus r t x t dt plus delta t times sigma e to the power minus r, sorry, this is I am putting it not x t but s t here. Now, we are bringing down substituting for d x t in terms of s t, e to the power minus r t s t d w t, which is again if you look at. So, this line if you look at it and if you compare with the previous line here. So, what you have d x t is given by this line here, right, this is the expression. Now, this d x t when you discount the first term, which is what we call the mean rate of return term, vanishes, right, and then the rest of the term remains. That is what these two terms, the second and third terms is what will give you this, and this could further be written down as e to the power minus r t s t, right. So, in a self financing wealth process or the portfolio evolution process, right, see the discounted value or the evolution of the discounted portfolio value process is simply due to the evolution of the discounted asset price process. There is no other component which contributes to this. That is what you need to understand from the last line that we have written from here. Okay. So, this is we have now done the evolution of the portfolio values, how the portfolio evolves from one time to the other, we have seen it. Now, the next thing that we will see is the option value evolution, right, or evolution of option value. Option value dynamics, okay, evolution means the okay, dynamics we can use the word so that the dynamics of the option value. Now, what we consider? We consider an European call option with payoff S t minus k, the positive part, which you know what is this? This is basically maximum of S t minus k or 0, that is what we know. So, this is payoff, this is at time t, which means the maturity or the exercise time for this European call option is capital T, and we are considering the interval 0 to t as the timeline, and payoff function is given by S t minus k, the positive part of it, which is basically the maximum of S t minus k or 0, whichever is the maximum, right. Now, this is the dynamics. So, the strike price k is some non-negative constant, right, So, what Black-Scholes, Merton and Black-Scholes and Merton argued is that, okay, at any the price of the call or the value of this call at any time t prior to its maturity should depend on that time and the underlying asset price process at that point of time. Of course, apart from the other constants that are involved in this, which is alpha, sigma, r and k, right. Apart from these, but out of all those things, since all these things k, alpha, sigma, r, these are all we are assuming constant for the interval 0 to t. So, the only two variables are the time and the underlying asset price, which in this particular case is the risky asset's price at that point of time, right. So, following that reasoning, suppose if we denote CTX, okay, as that's the argument that they had, denote, and later on you will see why that argument which they gave is actually true, right. Once now that you know little bit about stochastic calculus, we will see later that why that particular thing is true, right. So, but for the time being assume that this is the value of the call at t if st equal to x, okay. If the value of the European call at time t, if the value of the underlying asset is its value is 0, sorry, x, if that is the case, this is what. So, there is nothing about the random about this function, this functional form is known, the randomness comes through the x. X is if we replaced by the quantity st, corresponding quantity at any given point of time, then what you get is the price at that point of time, right, for that particular value of st. Now, since this st is a random process which could take any value in its state space, right. So, this total value CTST becomes random, otherwise, okay, if you look at the price process, okay. So, what is the price process in this particular case is basically CTST. So, the randomness comes through this ST, right. So, when you replace this x by its what you get is the price process, okay. Because ST is unknown in looking when we are looking into the future, so this process is unknown, but we know the functional form of this CTX. So, there is nothing random about the function CTX, but this process CTST is random process, right. So, that is what is the price process in this particular case here, okay. So, basically what we have, if we know the formula for it, then given any point of time, then we will be able to get the price at time t. That is what would be the thing that we might look for into the future. Okay. Now, our aim is to at least to get a formula for this function c, assuming that this is true. Okay. Now, I mean you know by now like why this CTX when x is replaced by ST is itself a function of t and x. Okay, we can give the reasoning now itself since you know stochastic calculus. We have seen that this price process ST is a Markov process because it is the solution of a diffusion type SDE, which we have said that the solutions are Markov process, and hence this ST is a Markov process, which even otherwise by looking at the expression for ST in terms of WT, you can know that this WT is a Markov process and hence this is a Markov process. So, for a Markov process for future evolution, all that you need is the time or the value of the process at that point of time. So, knowing only ST given the information of the filtration in terms of FT, which is the sigma field at time t in the filtration, right. Given FT, the only relevant information that you require for the evolution of this CTST is simply the value of ST, which is ST, and hence this is a Markov process, and hence this argument was right. I mean that is what is the reasoning why they have done this. Okay. So, now let us look at the differential of this, because we need to equate the how these two portfolio and the price process, right. We need to equate, by equating that only we form the set of equation to solve for this. Precisely same thing we are going to. So, we are going to look at the differential. Now, what is dCTST, which is essentially for this function CTST dt plus CXTST dST plus half CXX TST dST. Now, you can substitute for these two quantities, this and this, to get to this. What we get is basically CTTST plus alpha times STCXTST plus half sigma square times ST square times CXX TST. This whole thing is what is the dt term plus sigma ST CX TST dWT. So, what we did, dST we know the expression, dST multiplied by dST, it is sigma square times ST square times dt, that you plugged in. So, that gave you the third term inside the square bracket. The first term comes from dST, this is directly from here, this diffusion term comes from here when you put for the dST, right. This is what is the evolution of the portfolio value process, the portfolio value process. Now, we next compute the discounted value of this RT CTST. Again, we could think this as a function of the same ftx, which is e to the power minus RT times some x, where x is given by this CTST, right. So, this is essentially, you can think of this as d f of t CTST, okay, which is equals ft of t CTST dt plus fx t CTST of CTST, because our x here in this particular case is this C process, plus half fxx t CTST into dCTST times dCTST. Of course, the third term fxx is going to be 0. So, this will not make an impact here. The dt term which we have, dCTT, this term we already known, and fx and ft we already know. So, if you plug in that, what you would get is essentially the same expression, or similar rather, which t plus e to the power minus RT dCTST. Now, dCTST we have obtained earlier, right, and then you just have to plug in that with the discounted value, with the square bracket thing would expand, okay, would expand to write in this particular form. Let us write little bit carefully this. This is the term from here, previous line, but if I now substitute from dCT, from there I will get the remaining 3 terms here, which is basically right. So, this is the equation that we will end up with ultimately with respect to these two. The discounted portfolio evolution process is simply this. Now, what we have to do? We just have to, how do we find the position and the prices? Recall the discrete time model. We just have to equate the two evolutions. Okay. So, what we have is that a short option hedging portfolio starts with some initial capital X naught and invest in the stock market and stock and the money market account are the risky and risk free accounts, risk free assets, so that the portfolio value X t agrees at each time with the corresponding wealth process, right. The portfolio value agrees with the price of the option at that point of time, right. So, basically what we need is that a short hedge, short hedge. Okay. What is this? This is starts with some x naught, okay, and invests in the underlying assets, which is basically risky and okay. Underlying I would not use here because this has a different meaning. In the assets, in the market assets, okay, risky and risk free, so that x t equals C T S T for all t in 0 to t, right. So, this is what we want. If you do this, you start at each time 0, ultimately you want x capital T is to be equal to C capital T times S capital T, right. But how one way to do that is that if you make agree that at every time point this, of course, that is what the no arbitrage way of doing it, otherwise there will be arbitrage in the middle which one can take advantage, right. So, this happens. So, this is basically if and only if you can say e to the power minus r t x t is equal to e to the power minus r t t s t for all t, right. This happens only if and only if this. Now, one way to ensure this, what is this? Is to make sure that your evolution e to the power minus r t x t equals C T S T for all t in 0 to capital T prior to capital T, not including capital T, and make x naught equal to C 0 S naught. Okay. If we do this, that you can see by integrating this and by using the fact that x naught equal to C 0 S naught, right. So, by using this fact you would see that you will end up with the previous line that we are describing here, okay, and we get the desired inequality. Okay. Now, going back, now if we compare if we compare the expression that we have written here 1 and 2, one is for the discounted value process. So, comparing 1 and 2 that we have written down. So, what we can write is the following: delta t times alpha minus r s t dt plus delta t times sigma s t dw t is what one expression. The other expression is minus r c t s t plus c x t s t, sorry, not c x, did we write c x? No, c t. C t plus alpha s t c x t x t plus half sigma square s t square c x x t s t, this whole thing times d t plus sigma s t c x t x t dWt is what then you would get. If you equate this 1 and 2, what you get is this. So, 3 is what should hold. Now, what is required for 3 to hold, but comparing 1 and 2, if as per this process, one way to ensure that you achieve what you said to achieve is to do this starting with an x naught which is given by C 0 S 0 and making the evolutions equal, which means that these two must be equal. Now, what is required in order to make this hold? Okay. First, you look at dWt terms. Okay. dWt terms gives you what you have, delta t. If I compare the left side dW terms, okay, you look at term wise dW terms and you look at dt terms, right. So, you look at these two terms and then see if these two terms term wise if they are equal, then you are done, that is what you are trying to do. So, this delta t, if I compare delta t, sigma s t is here. So, delta t if it is equal to the C x t s t for all t in 0 to t, capital T excluded. Okay. So, this if this is true, if delta t is equal to this, then this is true that the dW terms would be equal throughout, right. So, this is called as the delta hedging rule, right. What this gives? Now, you can see that the position that you take, what you see from here is that the position that you take at time t is given by the first derivative of the function C A T S T with respect to S T, right. Now, recall even in the discrete time we had exactly same delta hedging rule. What was that? V n plus 1 h minus V n plus 1 t divided by S n plus h minus S n plus 1 t. You take that there is a natural 1 unit time steps, but now if you make the time steps to be infinitesimal quantity, then what you end up with this. So, it is exactly the same as that same delta hedging rule that you had it in the discrete time model, right. So, at each time prior to expiration, now what is the position that you need to hold is given by this delta t, and this quantity is what is called the Cx, is what is called the delta of the option. If you are looking for more of the Greeks, what they call in general, this is one of the Greeks and this is the delta of the option. What is the delta of the option? Means its position. That delta is what then you need to use it to construct a delta hedging strategy. What is the delta hedging strategy is precisely having this as your position. Okay. Now, next next look at dt terms, okay, dt terms, then what you would get is now delta t is given by Cx, okay, delta t is given by Cx term. So, the left side is essentially delta alpha minus r times St Cx, and the right side complete terms would remain the same. So, what you have is alpha minus r St Cx Txt, which is equal to minus r C times Tst plus Ct Tst plus alpha St Cx Tst plus half sigma square S square T Cxx Tst. This is for t in 0 to this. Okay. This you can now cancel this alpha term on both sides. You can just cancel this alpha terms on both sides. So, you are left with only the remaining terms, which actually gives us r to for all t, for t in these things, right. So, what we need, this needs to be satisfied. We want a function that is satisfying this in this interval, and also the so and also satisfying the condition that at time capital T what is we require, right. So, in essence, right, in conclusion, what we need is that we seek a continuous function, say Ctx, that is a solution of solution to the what we call BSM partial differential equation, say PDE. What is that PDE? Ct Tx plus Rx Cx Tx plus half sigma square x square Cxx time Tx is equal to R Ctx for all t in 0 to t x greater than or equal to 0, and that satisfies the what we call as the terminal condition C T x equal to x minus k, the positive part. So, all we need is basically this is the BSM PDE that we have. So, this is the solution to this BSM PDE, which is what is given by this and this. So, if we have, okay, suppose we have found this solution, right. Suppose if you have found the solution to this BSM PDE, then and what we have done, if you start with, okay, suppose if we have the solution, okay, suppose we have the solution, right, suppose we have the solution, then we can start with say an x naught, which is given by C0 S 0, and adopt what and use the hedge rather than, and use the hedge delta t is given by Cx T S T, okay, then what we are going to have? So, then my x t is going to be C T S T for all t, okay, in 0 to t, for all t in this. Okay. Now, taking the limit as t increases to t, and the fact that both x t and c are continuous, right, are continuous, we can conclude, and x t and c t s t are continuous, implies that my x t would be equal to C T S T, which is S T minus K, the positive part, right. So, this means the short position has been successfully hedged by this process. So, what we need is the delta hedging strategy, which is given by this, but again for the delta hedging strategy C x you need the function C. So, if you can solve this PDE, if you can solve this PDE by some means to get the functions from CTX, then you have everything, that the stock price process or the derivative price process at time t is given by CTST, and the hedge is basically the first order derivative with respect to x is what would give you this. Now, what is the solution? Okay. We will see this and then we will end. So, this BSM PDE solution to BSM PDE. Okay. So, we are not going to solve this solution the PDE right now here, because later on we will give a different way of solving this, but you can even solve this BSM PDE and then get the exact same expression that what we are getting here. Okay. So, that is you can take. Okay. Now, what we want is the BSM PDE to hold for all x greater than or equal to 0 and for all t starting from 0 including 0, but up to t, but excluding capital T, right. So, that is what it is the case. So, but we know that if x is 0, then this is going to remain 0 throughout the stock price process. If x is greater than 0, so the stock price process is going to remain positive throughout, okay, right. So, those informations is what then we might use to look at that. But before starting of that, so let us specify whether the condition that is specified here with respect to the PDE and the terminal condition is sufficient. Yes, if you look at, this is a backward parabolic PDE, right, and which for such an equation you also need the in addition to the terminal condition, boundary conditions at near boundary conditions at x equal to 0 and x is equal to infinity. Okay. So, we will see say some such condition that we have to develop in order to solve this PDE. So, let us briefly give this. Now, if you substitute x is equal to 0 in the PDE, okay, with x is equal to 0 in PDE, you will get as C t t 0 as r times C t 0 is what is the expression that you would get. So, this is an ordinary differential equation which with solution as e to the power r t C 0 0, right. Substituting this t is equal to capital T, because this is again should satisfy that t is equal to capital T. So, which means that for t is equal to capital T, what you would get is C capital T 0 is essentially 0. So, that implies C 0 0 is also 0, and hence okay. So, this you do not need, and hence okay, from here we are moving to here, and hence what you would get, and hence your C t 0 is 0 for all t in 0 to t. So, this is one boundary condition which is x at 0. Now, as x tends to infinity, the other boundary condition that we might look for, is essentially if you look at x very large value. So, this in that case the Ctx also grows without bound. In such a case, we give the boundary condition by giving rate of growth at infinity, by specifying the rate of growth. This is basically we are saying by giving this condition, this Ctx minus x minus e to the power minus r t minus ttk, this is equal to 0 for all t in 0 to t. Okay. So, in particular what we are saying is Ctx is growing at the rate as x, because for large values of x, because the European call is going to be very deep in the money, and the deep in the money is exactly same as x, because x minus k the positive part, no matter whatever be the value, for x very large, x minus k positive part is almost equal to x. That is precisely what we are saying by this condition, right. So, with these two boundary conditions, then the solution is given by, so we have a BSM PDE with one terminal condition and two boundary conditions. The solution is given by, we simply give the solution, later we will try to prove or obtain or derive the solution here. X minus k e to the power minus r t minus t n of d minus of t minus t x for 0 less than or equal to t less than or equal to less than capital T, and for x greater than 0, where my d plus minus of set some tau x is essentially 1 over sigma over tau log x by k. When we write ln, it is to the base e, or plus or minus sigma square by 2 times tau, and n is the CDF of a standard normal distribution, CDF function of normal distribution, which is basically n of y would be 1 over under root 2 pi minus infinity to y e to the power some u square by 2 times du, right, which you also know is also same as 1 over under root 2 pi minus y to infinity e to the power minus some t square by 2 times tt, right. This is what you would see from the properties of the normal distribution. Now, what we see here is that, so sometimes we shall write sometimes, because this we are going to need later, as BSM tau x and k r sigma as x n of d plus tau x minus k e to the power minus r tau n of d minus of tau x, okay, and call this as the BSM function or BSM formula for the European call option price, okay, BSM formula for European call, right, is what we call, this is for notational convenience, but tau is means, okay. So now let us look at this. Of course, this is a solution that we have written down here, which is given in terms of some quantities d plus d minus. In some books you would find d1, d2 they will use, does not matter, it is only the notation. There are two quantities, and n of d plus and n of d minus is what the normal CDFs replaced in this manner, right, and this is what is the expression that we give, right. So this is what then you would get. Again, if you look at here, the solution is given for not at t small t equal to capital T and x is equal to 0, right. And in both the cases, of course, they are defined by continuity of the function, so that it can be verified that the solution which is satisfied by continuity, if you define, what you get actually is what the solution that you would get here, okay. Now this one, the delta hedging strategy here, which we set that CXTX in this particular case will turn out to be n of d plus this. We can this is an exercise, you can try that the delta hedging strategy is actually is given by this quantity. This is the explicit form of the delta hedging strategy that we have got now for this formula, okay. So this is what we have discussed the APT approach or the replication approach to pricing an European call option in the Black-Scholes-Merton model. We will later put it up in the risk neutral framework and continue further in the next lecture. Thank you.